This lecture is on Lenz's law. So Faraday's discovery of induced current opened the door to readily accessible and cheap sources of current. This current can be used to power electric motors and other devices, saving time and money for many people and industries. However, there are still some questions to be answered. What determines the direction of the induced current? And where does the energy associated with induced current come from? Consider the case of a north pole of a magnet being pushed into a coil. When the north pole of the bar magnet enters the coil, the galvanometer indicates an induced current through the coil. When the north pole is removed, the current is shown in the opposite direction. So we push the bar magnet in and then pull it out. If we use the south pole, the current is induced in the opposite direction. And again, when you pull out with the south pole, the direction of the current reverses again. Evidently, there's some simple relationship between the action of inducing the field and the direction of the induced current. In 1834, a few years after Faraday's discovery of induction, a German physicist working in Russia, Heinrich Lenz, applied the law of conservation of energy and succeeded in stating his relationship, which is now known as Lenz's law. Heinrich Lenz discovered that when a current is induced through a conductor due to a changing magnetic field, known as an inducing field, the induced current sets up a magnetic field known as the induced field that opposes the motion of the inducing field. For example, if the north pole of the bar magnet is inserted into the core of the coil, the induced current in the coil creates a north pole at the right end of the coil, and it opposes the motion of the magnet. A similar situation occurs if the south pole of the bar magnet is removed from the core of the coil. So the changing magnetic field really produces an electric field, and the induced current is just the way that that electric field is detected. So Lenz's law: for a current induced in a coil by a changing magnetic field, the electric current is in such a direction that its own magnetic field opposes the change that produced it. So it is the work done in moving the magnet against the opposing force that is transformed into electrical energy in the induction coil. So there's a conservation of energy in that sense, because we're doing work by opposing the force of the two fields. Determine the pole of the bar magnet that's being inserted into this coil as shown. So if we're moving in that way, your fingers would curl up around that, and your thumb would point to the left. So that means that that field must be a south pole that's moving in. Determine the direction of the current in the coil shown. So here, it's already shown for us. Our hand would be pointing, curling around left ways around that. Our thumb would be pointing down, so it must have been a north pole that was moving through. Conductors are being pushed to the left in each of the following diagrams. Use Lenz's law and the right-hand rule for straight conductors to determine the direction of the induced electric current. So for this question, you can try this on your own, just showing the direction. It's kind of hard to show these right-hand rule questions, so I'll let you try that and let me know if you're having trouble. Here we have a magnet being pushed into a coil to induce a current. The magnetic field that is created never attracts the magnet into the coil. Explain why this is the case. So one application of Lenz's law is with drop towers that we see in amusement parks. So the braking system that's used is actually a system that relies on electromagnetic induction, and we can explain it using Lenz's law. Each cart on the ride has permanent magnets underneath the seat, and after approximately 45 meters of free fall, an electromagnetic braking system kicks in. Along the bottom third of the tower are copper strips that are mounted vertically on the tower. When the cart falls and the permanent magnets move past the copper conductor, an electric current is induced in the copper. The induced current then produces a magnetic field. And applying Lenz's law, the induced magnetic field must oppose the field that created it. So this opposing repulsive force creates a non-friction braking system.